So let's talk about some applications of Bernoulli's equation. Let's manipulate it a little bit. So we were looking at our diagram here, and we said that the energy down here must equal the energy up here. And we rewrote the total energy in the system in terms of work, kinetic energy, and potential energy, gravitational potential energy. But let's take a look at what that means. So in this case, what I see in this diagram is that, first of all, y1 is less than y2. So I'm going to go ahead and write some things we know just by looking at the diagram. So y2 is greater than y1. Okay, cool. What does that mean, though, about the pressure and the volume, or excuse me, pressure and the velocity in the pipe? We can't tell those just by looking. So the first thing we remember is that we still can use the continuity equation. So Q is still constant, and it still equals A1 V1 equals A2 V2. Well, by looking at the pipe, I see that A1 is greater than A2. So, in other words, if A1 is greater than A2, what does that mean about my velocity 1 here? It means that, so if I'm looking at this case where A1 is greater, A2 is less, in order for these to be equal, I need my velocity 1 not to be greater, but I need velocity 1 to be less than velocity 2, so I get this compensation. So from the continuity equation, I know that my velocity over here is going to be less than my velocity up here. So these two things I have figured out just by looking and using the continuity equation. All right, well, what about pressure? How do I figure out which one is greater? Well, I can look at my equation here, and I say that V1 is less than V2, Y1 is less than Y2, rho is the same on both sides, G is the same on both sides. 1/2, of course, is a constant. So in order for these two to actually be equal, I need something over here to compensate for the fact that these components are less. So I need my pressure to be greater on this side. So in other words, I'm moving slower, I'm at a lower height, but I have a greater pressure down here than I do up here, which makes sense. So we figure that out using Bernoulli's equation. Let's look at another case. Let's consider a flat pipe. So, in other words, we have a pipe that is horizontal, but it has differing widths. So we can look at area 1 here, and we can talk about area 2 over here. So since it's a flat pipe, we can say that y1 equals y2. All right, that's great. And what I want to know is, what can we say about pressure and velocity in this system. How can I talk about pressure and velocity over here versus pressure and velocity in here? Well, since y1 and y2 are equal, that means I can take Bernoulli's equation and I can cancel out these two terms entirely. So I end up with P1 equals 1/2 rho V1 squared. Oh, excuse me, P1 plus. And that equals P2 times, or excuse me, plus, goodness, 1/2 rho V2 squared. So I've rewritten Bernoulli's equation. I'm interested in pressure and volume, or excuse me, pressure and velocity. So how do I go about this? How do I go about thinking about this? Well, first of all, I still hold to my continuity equation. That part doesn't change. And so I still know that Q is a constant. So A1 V1 equals A2 V2. In other words, what I know is that if I let this side of the equation be my initial condition, I increase my area, so that means I decrease the velocity in this region. So, in other words, I know that V1 is greater than V2. Okay, so I know that from my continuity equation. So I can talk about the relative velocity. How does that affect pressure? Well, if V1 is greater than V2, and these have to be equal, both sides of the equation have to be equal. This isn't changing, that's not helping. So in order to compensate, I have to mess with my pressure. So my pressure in this region is less than the pressure in this region. So what that means, again, we're looking at a case where P2 is greater than P1. So let's talk about those implications. Effectively, what that means is that, all things considered, wherever I have a case where my velocity is greater, that means I have a region of lower pressure. So I'm moving faster, but I have lower pressure. We need to be careful that we're not confusing pressure with velocity, because pressure has to do with the force felt within the fluid. This is dealing with the work done by the fluid. Velocity is how fast we're moving. So again, it seems a little counterintuitive, but think of it this way. If we have high velocity, what that means is we have stuff, we have fluid, matter, moving out of a region quickly. And if that stuff is leaving the region quickly, what that also means is, remember, pressure is going to be related to the density. As stuff leaves the region, that's going to draw anything nearby back into the region. In other words, you can kind of think of it this way. So the limit of low pressure, as pressure gets lower and lower and lower, we call that vacuum. Vacuum is just a region where pressure is zero or very, very low. So if we think of it that way, then we can say that nature abhors a vacuum, which is true. And nature will try and fill that vacuum. It will try and fill a region of low pressure with whatever is nearby, kind of drawing whatever is nearby into that region of low pressure. A more correct way, actually, to think about that is rather than saying the low pressure is drawing something in, what we really have is a case where we have low pressure and there's a region of high pressure surrounding it that is pushing everything into that region of low pressure. Nature likes to be balanced. And so it's not so much that low pressure pulls from high pressure as it is from that high pressure regions push into lower pressure regions. And so what that means is if you have high fluid velocity, like in this case here, what that means is you have low fluid pressure. And we're going to play with that more in class. But again, what I'm wanting you to see is that low pressure is related to high velocity of a fluid. Something that kind of trips us up a little bit is we imagine a garden hose. And when we have water coming out of the garden hose, when it's just plain, when we have a large area, if we have a large area, what that means is we have a slow velocity. And so water kind of comes out a lot at once, but when it comes, the flow of water looks something like this, because it's coming out with some velocity. And by comparison, we can talk about a water hose that has an attachment to make the water come out faster. So we're looking at a small area and a high velocity. So in this case, we get water spraying much further before it starts to fall. So we consider this, in our heads, we think about this as being a high pressure situation, but really what we're looking at is a case where we have high velocity. So our velocity is greater, but the pressure within the fluid itself is not. Okay, I'm not talking about the pressure I feel against my hand. What I'm talking about is the pressure within the fluid itself. And so here we have actually high pressure within the fluid because it's moving more slowly, compared to this case where the pressure or the water is moving quickly, and so this is actually going to be low pressure within the fluid, not so much the pressure you feel if you were to stick your hand here versus sticking your hand here. So there's a difference. The pressure we're talking about in Bernoulli's equation is the pressure within the fluid. Okay, it's the work done on the fluid by the pressure within the fluid itself. So it's important that we make that distinction. And the last thing we're going to touch on as we're discussing fluids is a viscous fluid. So we said earlier that we're mainly dealing with ideal fluids and ideal fluids are non-viscous. But in reality, we deal with viscous fluids. And when we start talking about fluids that have viscosity or fluids that have turbulence, that's where we get more complicated. And being as this is not a fluid dynamics class, I'm just going to kind of give you the quick and dirty when it comes to dealing with viscous fluids. So if fluids aren't allowed to flow freely, that means there's something within the fluid kind of fighting that flow. So there must be something that allows the fluid to continue to flow. So there has to be something external going on. And that external bit that allows viscous fluids to flow is a pressure differential. So, in other words, we need a change in pressure. And hopefully it doesn't take a whole lot of imagination to see that we would need to go from a high pressure to a low pressure. That's the way that fluids flow, is from a high pressure to a low pressure. And so what that might look like is if we have some pipe and we have a viscous fluid within the pipe, what we've got is some difference. There's a change in pressure between these 2 points. And so I might have over here, if we're flowing this way, I can say my pressure at this point is going to be my pressure plus whatever this difference is. Whereas over here, I'm just looking at this pressure P. So in other words, what I'm saying is that we have to have a high pressure on one end and a low pressure on the other in order to get viscous fluids to flow. So we need a change in pressure, a pressure differential, a difference in pressure. We also need to understand that because of this friction that's present in viscous fluids, we're not going to have the same velocity everywhere in the pipe. So we're going to have maybe a low velocity on the edges and a higher velocity in the middle. So the idea is wherever there are edges or things to catch on, it's going to slow our velocity down. It's going to slow our flow down. And so when we go back to talking about the continuity equation, what we have to deal with is we have to use an average velocity. So what that looks like is in our continuity equation, Q equals the average times my area. So area, remember, is going to be this, for a round pipe in particular, is going to look like pi r squared. And there's actually a whole lot of factors that play into this average velocity. And the book does a decent job kind of talking about where some of those components come from, but ultimately we don't derive it in the scope of this class. And so what I'm going to go ahead and give you is, I'm going to butcher the French here, but it's Poisson's equation. We'll go with that. Make sure I spell it right. Okay, so I want to make sure it all shows up. So this equation, in its final form, is just an extension of the continuity equation, but we've like I said, kind of substituted in some factors for V average and area. So Q equals V average times area. But what that ends up looking like is pi r to the fourth times this pressure differential divided by 8 times eta, that's our viscosity, times L, where this distance between ends of the pipe is L. So real quickly, what that looks like, what that means, is that the more pressure differential I have, the greater average velocity I can have through my pipe. Okay, so if I have a higher pressure and a lower pressure, I can get faster speed, so a greater volume flow rate. If I have a longer pipe, that means I have to be flowing for longer. I'm going to slow down the longer I'm flowing. So that means a lower volume flow rate. If I am more viscous, that means it's going to slow me down more. So I have this inverse relationship here between length and viscosity versus my average velocity. Now, we said the pi comes from the area part. We had r squared, but now we're dealing with r to the fourth because not only are we seeing it in the area, but we're also seeing that my size of my pipe is also going to be related to the velocity. Because if you think about it, if I have a nice large pipe, the edges aren't taking up as much space, or rather fluid along the edges are not as common as fluid inside. So I get better flow. But as my radius decreases, the amount of fluid that's touching an edge increases. So in other words, if I have a smaller radius, I'm dealing with my edges more. And when I deal with my edges more, I get hung up. I slow down this average velocity. So a smaller radius means a smaller average velocity, greater radius, greater average velocity. And it also affects the area. So what this is saying is that I'm highly dependent on the size of my pipe when I start dealing with viscous fluids, way more so than I was when I was just dealing with a nice non-viscous fluid before. So this is an equation that you may or may not see when you're studying for the MCAT. And my main concern is that you know what the different parts of the equation mean and you know how to use it. That is my main concern for what you understand in terms of fluid viscosity.